Okay, so we're continuing with Gauss's law here, doing some fun derivations. And so far we've learned how to find the field due to a point charge and due to an infinite line of charge. And we've now used the two tools that we're going to be using almost all the time to do Gauss's law problems, and that is to analyze situations that have spherical symmetry, like the point charge, and situations that have cylindrical or linear symmetries. Those aren't really the same thing, but I'll pretend they are radial symmetry, such as the infinite line of charge. And so, gee, what else do we do? Well, the other thing that we do is we make those situations more complex. And we do it sometimes in bizarre, aka unrealistic ways. And so I'm going to do a couple of these. I'm going to go a little faster than I did in the last one because we like going faster. So I'm going to introduce you to the basic situation. I'm going to give you a situation with spherical symmetry, but it is more complicated than a single point charge. This is a sphere, a solid sphere of radius r, big R. So this is, remember, a solid sphere, trying to draw a 3D perspective. And I'm going to tell you that this sphere is made of plastic. It turns out, for reasons that we'll see in another day or two, that it's important to note that this sphere is an insulator. And I'm not going to pretend that you know why that's important right now, but it's important because it means that what I'm about to tell you can possibly be true. And what I'm going to tell you is that this thing has uniform volume charge density. So basically what it means is that every cubic centimeter has the same amount of charge as every other cubic centimeter of plastic in this, like it's a bowling ball. And it's been charged throughout, not just on the surface, but throughout. The whole thing has net charge. As I say, maybe unrealistic, who cares? We're going to do this anyway. And what I am interested in doing is finding the charge at a couple of different points. One is at point P, which is within the sphere. And so this point P is distance little r from the center. And the other one, which I may or may not even do, is a second point P, I'll call it P prime, which is a distance also variable r. I'll call this r prime. But a point which is outside of the sphere. Okay, I'm going to do the first one first because I call it the first one. And so here we go. What is the electric field at point P within the sphere? Okay, first of all, we're going to say that this uniform charge density is positive, and for symmetry reasons that I made in the last video, the field is radially outward. The field at that point is radially outward because this stuff inside here has positive charge. The stuff inside here meaning the charge closer to the center than point P. That's going to be relevant for reasons we'll see in a second. By the way, the shell theorem, if you're thinking shell theorem, and if you're thinking about the problem we did with a tunnel going through the Earth and finding the gravitational field at points within the Earth, good, because it's a very similar kind of a problem. And Gauss's law and the shell theorem are good friends. And so some of the conclusions that we made of the shell theorem and stuff that we're going to see with Gauss's law are consistent with each other, which makes us happy. Okay. So what is the electric field at point P? All right, now we're going to go fast, believe it or not. Can he go fast? I don't know. Well, let's find out. Step one, define a Gaussian surface. My Gaussian surface will be a sphere of radius little r concentric with the big sphere, which I know is the big sphere because I'm writing it in big letters. Okay. And I've basically defined it with this green circle here, although this Gaussian surface has, I'm trying to draw that in 3 dimensions. So the Gaussian surface is that sphere. Good. Now I say, what is the flux through that surface? And I say the electric flux is surface integral of E dot dA, and vector, vector. And I now say, okay, all my area vectors point out from that, and at point P, my dA vector is parallel to E. So I say everywhere E is parallel to dA at every point on that surface, because everything points radially out, which means I can get rid of the dot product, and due to symmetry as well, E is uniform everywhere on that surface. There's no reason it should be stronger one place than another, because I'm always r away from the center. And so therefore, this now turns into E times A. This is getting fairly painless now, isn't it? Okay, because of these two things. So this makes the dot product go away, and this makes the integral go away. Because E gets pulled out, and I'm just integrating dA, which is A. Okay, now I write Gauss's law. We're almost done, believe it or not. By almost, I mean almost. I write Gauss's law, which is flux is equal to Q enclosed over epsilon naught. Ah, how much charge is enclosed inside this thing? Okay, the charge enclosed, Q enclosed, is equal to rho times volume. This thing has uniform charge density, which is, of course, Q over V. All right, and you know what I actually want to do is I want to go back in time. Haha, this is lame, and I want to say at the beginning, the whole thing actually has charge Q. Okay, so this Q is actually a given amount. All right. And this is the volume of the whole thing. So rho, in fact, is equal to big Q over 4/3 pi big R cubed. All right. Because I have to be very careful. I'm trying to go too fast. This volume is the volume of the little sphere. So volume, I can do better than this. The volume enclosed within the Gaussian surface. Volume within the Gaussian surface. And so Q enclosed is rho, which is Q over 4/3 pi big R cubed, times the volume within the Gaussian surface, which is 4/3 pi little r cubed. And guess what? My 4/3 go bye-bye, my pi goes bye-bye, and Q enclosed is just Q times R cubed over big R cubed. Okay, now we're almost done because now I've got flux is EA, so I'm going to write EA for this flux here. This flux I'm subbing at EA equals Q enclosed. The Q enclosed is big Q times little r cubed over big R cubed over epsilon naught. Okay, what's the area of that Gaussian surface? It's a sphere, so it is 4 pi little r squared. So E equals, I'm going to move the area over here, and the area is 4 pi r squared, and I've got an epsilon naught in here, which you notice I tucked in next to the 4 pi because it looks cool. And then I have up on top, so that's the bottom. Now up on top I have Q times little r cubed over big R cubed. Okay? I simplify because I've got a little r cubed on top and a little r squared on the bottom. And I end up with the electric field is 1 over 4 pi epsilon naught. I choose to write that out in the front, times big Q, got the big Q, over big R cubed, and then I still have this R hanging out there, times R. And that is it.